Hi, I thought I'd post this video of this neat little Z80 test circuit I've been playing around with. Now, this is not original. This test circuit is quite well known, and I'll post a link to z80info.org with some schematics of a similar circuit so you can see it in more detail. Now, I was watching a video on another YouTube channel, Julian Eilert. He has a nice channel where he posts all sorts of interesting and fun videos about electronics and computers. I'll post a link to that too in the description. Anyway, earlier this year he posted a nice little circuit like this which got LEDs flashing, and I thought I'd set it up myself and look at this in a little bit more detail. Now, I'm running this at about 1 Hertz, and the reason I'm doing that is because I want to be able to see precise timings of the opcode fetch cycle. And the opcode fetch cycle is described in the Z80 user manual, which you can download for free, the original Zilog one, and I'll just give you a quick look at the timing there. And that's the activity on the various pins on the Z80. We have LEDs attached to most of those pins, so we can see that timing in real time. Normally you would need an oscilloscope or something, because the Z80 doesn't normally run at 1 Hertz, it runs at 2.5 million Hertz on the most basic version, which we have here. Well, let's explain what we have here. We have the Z80 there. That's the original Zilog Z80 at 2.5 megahertz. I got that for about £4 off eBay, and that's running at 5 volts, of course, off a USB power bank, and that's very convenient. Other processors needed 12 volts and such. You know, USB wasn't invented when the Z80 was invented, but here we are today powering it with just a USB power bank. Isn't that nice? And as you can see, the circuit's drawing about 0.05 amps, 50 milliamps. It's been running for about 5 hours. It's very stable, this circuit. I've had it running for a couple of days. It doesn't seem to crash at all. And there are people who claimed, when I was researching this, that these older Z80s are made with something called NMOS technology. I'll let you look that one up on Wikipedia. I don't want to say something incorrect. Yeah, they claim these older chips wouldn't be so stable at low frequencies. I mean, one of the nice things about the Z80 is the status registers are held in static RAM on the chip. So in theory, as long as power is supplied, the status registers should hold their values. And now, the specification doesn't guarantee that at such low frequencies as this for the original Z80s, but for the newer CMOS Z80s, they apparently do guarantee that, and you can just single step through cycles 1 a day or something if you wanted to. This is a 6 megahertz rated CMOS Z80 from 1999. But I don't want to test a CMOS one because I have a feeling the pins aren't as tolerant to running these small currents to power the LEDs. I think I have read that the older NMOS Z80, the pins are tolerant to about 10 milliamps or so, which is you know, good enough to light these LEDs. I've got 560 ohm resistors in series with these LEDs to limit current, at least on the red, yellow and green ones. The blue and the white LEDs on the clock pin of the timer chip, NE555 timer chip, I've got 3.3k kilo ohm resistors on the blue and the white, and that limits them down to a milliamp or less even, and that's because they are so bright. If you put anything more through them, they really are very bright compared to the red and yellow green LEDs. Now I was thinking of not using blue and white LEDs because I was going to say here we are with 1970s technology, and of course blue LEDs weren't around then, but yeah, let's not be silly. I mean that Z80 is from 1984 anyway. Right, so okay, that's our Z80. Now what to explain about this? This circuit, as I say, is a classic test circuit. It executes no ops continuously. No ops are instruction opcode 0, and you get that by bringing all the data pins to ground. That's through 1K resistors there, and they're all pulled to ground, so that gives you 0 opcode, which is a no op. And what we're going to demonstrate is the 4 cycles required for each entire opcode fetch cycle. So the entire opcode fetch cycle requires 4 clock cycles, and we can see that very clearly here. The red LEDs are attached to the address pins. These are A0 to A6, the lowest 7, and then we have A7, A8, A9, A10. It does go up to A15, but I didn't want to connect all of them. This is enough to see what's going on. What you will notice is that the higher address pins here, they seem to be flashing on and off every 2 cycles, and you'll notice that this LED comes on when those go off. What's going on there? Well, this is to do with the refresh mode of the Z80. The Z80 would use 2 cycles to read from dynamic RAM, and it would set the refresh pin active when it wanted to do a read from dynamic RAM, and it would use the lower 7 address bits to specify an address from dynamic RAM, and it didn't bother using the rest of the address bus, so these would all go inactive, and I guess that saves a bit of energy. Now you might say, why use 2 clock cycles just to do fetch from dynamic RAM? Isn't that a bit of a waste? Other processors didn't do that. They would use an external, mechanism, but it's not actually wasting any clock cycles, because the Z80 uses those 2 clock cycles to internally decode the opcode. It's just fetched, so it has to use those 2 clock cycles anyway, and it just happens to do something extra at the same time. Okay, so that blue pin is connected to refresh. This blue pin is connected to the memory request pin, and that lights up at the same time as the read pin. Green is connected to read, red to write, and this yellow LED is connected to the M1 pin, and that pin goes active at the very beginning of the opcode fetch cycle. So if you want to count these clock cycles, you should start when the yellow LED comes on. 1, 2, 3, 4. 1, 2, 3, 4. And as you can see, when the M1 pin goes high, the address bus increments, and then just shortly afterwards, it's only about half a clock cycle afterwards, the read pin and the memory request pin go high, so that it then reads the opcode. The reason it waits a little bit apparently is because Z80 wants to make sure the address has settled, is stable in the memory, so it just waits a little bit. It's not a full clock cycle, it's just half, and you can see it very nicely at this speed. This is why running at this low 1 Hz speed is pretty nice, I think. You can see the timing if you look on that graphic I showed you at the beginning, or if you download the book yourself and have a look, you can really see that this cycle is very precise. It's incredible. This would be running at 2.5 million times faster than this. The precision of these things is just amazing. I just think this is sort of thing is underappreciated. I know it's engineering, but it's there's something of beauty about it. Now, one thing I forgot to say is, what are the other resistors doing on this Z80? There are 5 pins on this Z80 which can have external requests active on them, and they are active low. Now we don't want them active because we don't want the Z80 misbehaving, so we pull them all high, through 1K resistors. Now they are the reset pin, that actually is, I don't know if you can see the blue wire, that's actually connected over here to a micro switch because I want to be able to reset manually. If the Z80 crashes, often when you start it up by applying the power, it obviously starts off in a bad state and you need to reset it. You reset it by holding the reset pin to ground for 3 clock cycles. So I don't know, I'll do that now. So this is going to reset back to 0. All the red LEDs are going to go off. There you go. Now we're back to 0. Count 4, and then the next 4 cycles will go up to address 1, and then it will go up to address 2 after the next 4 cycles, and so on. Okay, so that's just handy to have that on a micro switch. So what was I saying? The 5 external request pins. Yeah, there's the reset, the wait pin. So some external devices will want the CPU to wait before executing the next opcode until some task was completed. And the bus request. Again, you might need have some external device requiring some bus request. So we don't want these becoming active. They interfere with the operation, so if we pull them behind, and there's 2 interrupt pins as well, the normal interrupt and the non-maskable interrupt. We don't want interrupts being generated randomly, so we pull those high as well. Now this is explained in the schematic from the test circuit on Z80info.org, so you can read about that there. Right, anything else to say? The NE555 timer, this is in the usual what's called a stable mode, so it's running at constant frequency, generating a nice square wave, which is perfect for driving the clock of the Z80. So that's the clock pin of the Z80 connected to the output of the NE555 timer. The output's also connected to this Arduino Nano on pin 8, and that's so we can measure the frequency. So we've got the signal being displayed on this white LED on the Arduino Nano OLED screen, this little OLED screen, really nice little screen for this sort of stuff, and also we've got the signal pin going there. So I've used all 3 connections above that pin there. Luckily I didn't need any more. And the values of this capacitor, the capacitor is 0.1 microfarads. That's across pins 1 and 2. On pins across pins 7 and 8 on the 555 we have a 1k resistor, and using those values it makes it nice and simple to calculate what we need for 1 Hertz. We need about 1440 divided by 2 times 720, so that needs to be about 720 kilo ohms. So this is actually a mega ohm pot, and it's in series with a 50 kilo ohm pot. This is so I can have a coarse adjustment and a fine adjustment, and these go across pin 6 and 7. This is very well known circuit anyway. You can look up the NE555 a stable mode circuit. It's extremely common. I'll adjust the frequency in a bit just to show you it actually works. And I think is that everything about the circuit I need to talk about. This top board could of course be completely detached. It's not necessary. This is a standalone test circuit. I'm just using I won't show some additional stuff here. I want to actually show the frequency precisely. I mean, you can see it approximately by looking at the light, but we're going to raise the frequency really high, and you can't see it flashes too fast to be able to see it, so it's nice to have a display. And also I want to look at these higher address pins to show you what happens during the 2 clock cycles when the Z80 is doing a dynamic refresh. So yeah, I think that's that. Let's talk about this Arduino. This is an Arduino Nano. If you're going to buy these, I would suggest buying them with the header pins soldered already. Fiddly to solder them yourself. You get these for a couple of quid from Japan, or a little bit more if you buy them locally. If you don't mind the 1 month wait, just order a few of them and go and do something for a month. This little OLED display, these are really nice displays. You can view them from almost any angle. They really are nice, even in bright light. So I like these. Also they run with hardware SPI, and you can get very fast updates with this. I've actually got some nice graphical stuff that I might show with this. I might even convert this into kind of an oscilloscope, but I'm not sure it will be so successful, but anyway, I'll have a think about that. But this is actually, I can get this running at 100 frames a second, updating the full screen, which is amazing really. And it's hardware SPI. Now luckily the pin 8 is not a hardware pin. The default software that comes with these OLEDs normally uses pin 8, but you can move it. So I've had to move one of the connections, which was on pin 8, to pin 6 or something, doesn't matter where, because I want to use the Arduino to measure the frequency. Now you can measure the frequency on the Arduino with various libraries, but by far the best one is one called Freq Measure, FREQ Measure. It comes with the standard ID, it should be in that library, and it uses hardware interrupt on pin 8 on the Nano and the Uno, I think, as well. Might be different pins on the other variants of the Arduino, and it uses a hardware interrupt routine to get a very precise measurement of the frequency. And I've checked this against the multimeter and it's very good. So I highly recommend, if you're measuring frequency, to measure with the Freq Measure library. I mean, there's code. I'll post the code for this. What this is doing is tiny. I mean, it's so easy to use. So it really is a nice library. I guess that's all to say about that. These, I won't bother posting links. If someone in a comment asks, I suppose I can find exact links to things, but these are very easily obtainable, all this stuff, and you're only going to pay a few quid. I mean, this whole lot together about 10 quid, you know. It's so cheap these days if you don't mind the weight from China. Otherwise you get about twice the price if you want to get it from a local supplier. Right, let's just increase the frequency now. That's nice to do at this slow speed, so we can see the opcode fetch cycle in real time and see the timings without having, needing an oscilloscope or something, which you would need to. And the only trouble with this, it is nice, it is beautiful, I've said all that, especially if you know what's going on. If you don't know what's going on, it might be a bit boring. You might think, it's a bit boring. So if you speed it up a little bit, let's go up to 10, 20, 30 hertz, yeah. Now it's a bit more funky for some people. I mean, look at that. Address bus updating. Ooh, it's really cool. And then when it gets to 127, it rolls over, and that's it's just waiting for that to happen is kind of hypnotic. And here we go. It's getting there. It's nearly 112. Rolled over, and that one incremented. Now, of course, at this speed, this looks like it's gone haywire. It's flashing all over the place, and these are all stable. But that's happening every 2 cycles in the 4-cycle opcode fetch cycle. These are going on and off, as we saw previously. This is why running it really slow, 1 hertz, is nice. You can actually see what's happening, whereas running it at just reasonably slow, you can't really tell what's going on. Right, anyway, let's just see how fast we can get it on this particular circuit. Now, of course, I don't think the NE555 is meant for 2.5 megahertz, so we won't be going up there, but with this capacitor resistor values, we can get up to about 1400 hertz, and let's do that. Oh, it's a bit low actually. It's just about 1200 hertz, 1200 hertz. Now you think, wow, that's really fast. Look at that little LEDs flashing away. You can't even see these LEDs flashing anymore. They look like they're continuously lit. But of course, it's still running at 1,000th of the speed of a normal operation. We're talking about 1970s technology here. 1976, 77, the Z8, the 2.5 megahertz Z80 came out. It's incredible that you can run these things at millions of hertz or 1 hertz. In fact, we can even run it at a fraction of a hertz. As I say, there was some question about the stability of these status registers as you get down to really low frequencies, but we can get down to about 3/4 of a hertz with this circuit. If I wanted to go slow, I'd have to change the pots and capacitor and stuff. Let's see, I think it's 0.75 of a hertz if I turn it right down. Yeah, so that's as slow as I can go, and you don't see much more that we see at the 1 hertz really. I mean, gets a little bit uninterested as you get slower and slower. You could also set up a stepper circuit to have people have set them up and you can just step through. If you really want to investigate complicated instructions, I mean, a no-op is not particularly interesting. You can investigate some of the more complicated instructions using accessing memory addresses and doing addition, and you might want to look at various outputs in, you know, without the CPU automatically stepping through. You would just have a little switch to step through. And as I say, the older NMOS technology CPUs aren't guaranteed to be stable, but this one seems to be. I mean, the ones I use tested all seem stable down to this about 1 Hertz anyway. Yeah, let's put that back up to 1 Hertz because I'm slightly anal about this. I think it's kind of just nice to have it run at 1 Hertz, isn't it? So that's the rough value. No, use the fine adjustment. Of course, I can't get exactly at 1 Hertz. I mean, there's a 1% error margin here. About 1 Hertz will do. Okay, yeah. So I should put this in a glass case really, and sell it as an ornament to go on people's homes. I mean, it's beautiful. I don't know. Kids today with their iPhones and Android devices. Back to the basics, guys. This is just beautiful stuff. And so cheap now. You know. If you don't mind the weight from China, that is. Okay, I'm using an old phone to record this at 720p resolution, and it's actually running out of memory, so it might cut out any minute now. Should I keep talking until it does, or should I cut it off cleanly? Did I forget anything? I was going to talk about using this Arduino. I mean, people might say, why don't you just use the Arduino for the timer clock cycle? I mean, it's more versatile. Well, I probably will eventually. I can remove all these components to do the timing, put the Arduino there. There's enough space, and I might do some more complicated experiments on the Z80. Oh, it just rolled over there, and I didn't talk about it. That was so cool. Right. So I don't know if you can read that Z80's sort of focusing properly. It's Zilog. What is it? Zilog Z8400 PS Z80 CPU 8416. 16th week of 1984 that was created. And did I show you the other chips? I tested it on this these Z80As. These run at 4 MHz. That one's fine as well. And I haven't tested the CMOS one. This is still in its pink anti-static apparently bag. I don't know if it is anti-static. It's just a pretty colour. Right, I think it's going to shut off in a minute now. The memory's almost 0. So I might post another video about with a little laser detector, Arduino and stuff. I don't think I'm very good at making videos though, so might be the last one, the first one and the last one. If anyone's got any interesting comments, please do post if I said anything incorrect or you have some extra interesting info. It would be really nice if you posted. I don't particularly have a channel to subscribe to or anything, but upvotes will always be appreciated. Well, I've got a minute to go, I think. Should I just leave that running? Could do some nice music, couldn't we? Dum da dum. No, actually, I better not start dum da dum. I mean, the YouTuber copyright algorithms will probably ban my video if I accidentally use 3 notes from one of the 5 billion pop songs that have been published. Yeah, I really might write a letter to the Tate Modern and tell them to set this up at the entrance or something, just to annoy people. Bit of engineering before you get to see all the art. You should go onto the Wikipedia Z80 page, and they have a photo of the die of the Z80 under a microscope. I know they have nanometer technology these days, but Wow, even that 1970s, 1980s technology is incredible. It's incredible that these things are so stable. They run so reliably. Right, okay, I'll shut it down so it's a nice clean ending. Thank you for watching. Bye.